multi-car collision avoidance. Oh, sorry, I just realized I've got the kind of toolbar thing at the top of the screen. Is that blocking your view of the titles?
No, for me, no.
Oh, great. Excellent. As long as you can see everything, that's fine. Excellent. Right. So yeah. So MUCA was this project for multi-car collision avoidance. So it's like cooperative vehicle behavior. And this was a project that took about 2.5 years. And although we were the lead partner, Cranfield was a significant technical partner. So there's quite a lot of kind of academic work done by Cranfield in terms of control algorithms and so on, and also development of neural network modeling. So I'll kind of mention that amongst our other partners. So that's what my connection with Cranfield is. It's through Marco, who was on the team. Oh yeah, sorry, I should say a little bit about us. So outside of our autonomous vehicle work, in general, we work on kind of vehicle electronics, any kind of software or hardware that goes into a car that's electronic. Some of those things we design as bespoke units, which I'll show you in the MUCA application. Sometimes we're working on other people's electronics. And in Cambridge, we're sort of mainly about software development, software testing, increasingly also about kind of functional safety analysis, safety of the intended function. I'll tell you, there's so much demand for jobs in that kind of area if you enjoy it, just as a tip. But the nature of our work is changing. So our headquarters is near Barcelona in Spain, and there we've got a big proving ground with lovely weather. It's got kind of a high-speed track. It's got a CAV testing area. It's got braking areas, all sorts. And our main business over there is that people come to use the track to test their vehicles. We support them in that. And that's what we're going to do in the UK, because we're building a new proving ground near Oxford. So that's going to kind of shift the center of gravity of our work. But I'll tell you about that later. So first of all, I'll tell you about MUCA. So this picture, still from the original bid, tries to explain what it was about. So firstly, I hope I don't disappoint you, but this wasn't like a kind of full autonomous vehicle project. I mean, the cars were fully autonomous, but these aren't kind of self-driving robo-taxis or anything. I mean, it's just such a big endeavor doing that unless you've got billions and billions of dollars to spend, like the Waymo and Uber and people, it's not really workable for just a small outfit. But we did just concentrate on one aspect which hadn't been done before. So seeing that cars in the future will have connectivity and also automated controls, steering and braking, we thought there was a gap in the market to use those things for a new kind of collision avoidance, a safety feature. So the idea was that you had a group of cars going down the road, coming up against obstacles, that they could take control, and it wouldn't really matter whether they were human-driven or being computer-driven at that point, but let's say the computers take control if they're facing a serious hazard, and they'd cooperate to get around the obstacles. They'd kind of work together. That was our vision. It always involves a lot of hand-waving like this. And so that was the real crux of the project, was to see if we could get cooperative behavior between multiple cars. And there's another aspect there, which was a real Cranfield thing. That an obvious kind of criticism of this kind of scheme is that you say, well, what happens if there's some normal cars there as well? They're not going to automatically cooperate. So the project's scope also included modeling where human-driven vehicles are likely to go, where the humans are likely to drive them. And that was modeled in Cranfield, and actually you being Cranfield, did experiments in simulator rigs to actually get volunteers to sort of drive in simulated situations, and then model that with a recurrent neural network. And so that was part of the project scope. Now I won't tell you much more about that because that was kind of the Cranfield part, and I can tell you more about the kind of vehicle part that we were more involved in. So I've said we wanted our vehicles to cooperate, and it's not at all obvious how you get them to cooperate. And when we started the project, I wrote a paper which, in retrospect, is mainly nonsense, for the Intelligent Transport Systems Conference, because at that point we were thinking we would need maybe like a voting scheme or something. If you had multiple cars with different ideas of how they should resolve the situation, that they'd have to kind of have a conversation almost, and maybe they'd have to like rank their different solutions to how to avoid a collision, and then get everyone to follow someone's plan. And then we're worried about what happens if the plan changes with time. But in the end, we didn't do any of that. We did something much simpler, which I'll show you. So hopefully I've got an actual simulation here. If it still works, haven't run this for a while, then I can show you how our cooperation worked. So what we ended up doing was having a scheme where each vehicle kind of shared its plans with all the vehicles around it. So it shared its plan of where it was intended to go, but also it would share its plan of where it wanted to go, even if it couldn't because there were other mucker vehicles in the way. So that's the planned and desired trajectories. So we call this the desired versus planned approach. And it's not something we invented from scratch. We actually got the idea from a cooperative lane merging scheme that's been proposed in an EU project called TransAid. But so we've kind of hijacked it for collision avoidance, where instead of just being about lane changes, it's about vehicles going anywhere they like across the road and in any number to avoid collisions. So I'll just show you. So we've got these two cars. These green rectangles represent mucker cars, hence the M. And they are, let's say they're bombing down the motorway, and they're just coming up against this HDV, the human-driven vehicle, which is in the slow lane of the motorway. So at this instant, they see it with their sensors, and they think, oh no, we've got a problem. So obviously the M1 vehicle has the real problem because it's on a collision course. M2 is fine because it's currently aiming to go past it. So this is where the trajectory planning comes in. So we give it a step so they can kind of think about what they want to do. So M2 is still absolutely fine. It's got no reason to do anything other than go straight down the road. M1 has two completely different plans. Its actual plan for what it thinks it should do to be as safe as possible, knowing everything that it knows immediately about the other vehicles present, is just to brake. So these blue blobs getting closer to each other indicates a decelerating trajectory. And given that the human-driven vehicle will have moved along a bit by the time it gets there, it will hopefully just avoid collision, or it'll at least minimize the intensity of collision if it does. But that's not what it wants to do. What it wants to do is to steer around the human-driven vehicle. So these pink crosses show that it would prefer to go around. Now, the connected bit here is that they then trade these plans over vehicle-to-vehicle radio. And having traded plans, they can then update their plans at the next iteration to take account of what they've now learned about what the other vehicle wants to do. So if I just step once, so at this iteration, the last thing M1 knew was that M2 wanted to go straight. So it's still planning to brake because it thinks otherwise it will run into M2. M2 though, because it knows that M1 would like to swerve, can say, oh right, well actually, there's no real cost to me of swerving out the way, so I can do that. So it's replanned its trajectory, but it hasn't yet communicated it. And then on the next instant, we again trade plans over the radio. And in real life, that wouldn't be time synchronized. So now M1 knows that M2 is planning to move out the way. So now it can replan and say, oh, great, now I can plan to go around the slow vehicle. So then if I just press play, they should both get around. So, the example is pretty simple, but what we ended up with were two vehicles who had never spoken to each other before, and neither of them was in charge. Neither of them was really dictating what the other one did. They were both just sharing their plans, but kind of accommodating the other car if they could. And we ended up with cooperation. We ended up with a cooperative swerve. So that was just that kind of cooperative movement that we envisaged when we were kind of bidding for the project. where they kind of acted together. And that would be quite difficult for humans to do. You know, I suppose you might manage if you're kind of looking over your shoulder going along, thinking, oh, is that person going to move out of my way? But, you know, it would be pretty hairy. Whereas here it was achieved automatically. So, and that was the crux of the algorithm. And if I just reset, we don't have to just have 2 cars, we could have 3 cars. And we have the same sort of thing. So now M1's saying, oh, I want to swerve out of the way, but I'm going to plan to brake. Then M2 says, well, in that case, I would like to swerve out of the way, but I can't because M3's there. So I will just plan to go straight on, but I would like to steer if I could. And unfortunately, in this case, of course, M3 is kind of boxing M2 in, and that means M2 is boxing M1 in. So we don't have a kind of cooperative swerve available. And if I press play, M1 will eventually be forced to sort of brake as hard as it can. M2 and M3 can get past all right. And it's going to be pretty close for M1. And oh dear, right, okay. So obviously that wasn't a good outcome. But if we give it another lane, and try that again. So now M1 says I want to swerve, M2 says I want to swerve, M3 says, okay, I can do that safely now. And they all get round. So that was the algorithm. So just sharing the desired and planned trajectories and accommodating each other. That's how we kind of solve the problem. So I'll just go back to the slides. Oh, there's a video. So there is a version on YouTube. So if anyone was looking at these slides offline, then they'll be able to play that. Sorry. Right. So the actual solving of those trajectories was through model predictive control. So for those who haven't encountered it, the idea is that you have a sort of cost function that measures the goodness or the badness of your future trajectory. And the actuator outputs that control your vehicle are in effect the variables, the independent variables that you can apply as a function of time. So you might say, well, in 1 second I will be steering to the right, in 2 seconds I'll be steering to the left, in 3 seconds I'll be going straight on. And you kind of throw the actuator outputs, the variables, into a numerical optimizer. The cost function is then minimized by avoiding things like overlaps between vehicles, and you end up with an optimal trajectory that you can achieve given real actuator outputs. And then you apply whatever the immediate outputs should be and throw away the rest of the solution and do it all again in another time step. So that's how we plan the trajectories. Now the version in the vehicle was pretty simple, but at Cranfield, Marco's colleagues did some much more advanced versions with more fancy solvers and 2 levels of MPC, like one for trajectory planning and one for trajectory tracking, and a much more complicated vehicle dynamics model, which we didn't have. So within the scope of the project, there was a lot of quite detailed work done here, but the version on the vehicle was relatively simple. Yeah, I'll just go on to the next couple of slides because that'll explain things better. So we want to avoid the cars overlapping because that's a crash. But what we didn't want to do is, sometimes people put that in as a constraint when they're doing kind of cooperative work like this, so that the solver will not return a solution that ever results in vehicles overlapping, which sounds like a good idea. But if you're in a real vehicle, you might find yourself in a situation where a crash is inevitable. You don't want to ask the solver, what do I do now? And the solver will just say, sorry, no solution, mate, because you've got to do something. So instead, you've got to have a finite cost to crashing that is, it's expensive, but your solver will still return a sensible solution, and that solution is like to be brake as hard as you can to minimize the cost. So we used kind of sigmoid functions like this to make a kind of box of potential that kind of discouraged the vehicles from overlapping. There were some similar things for preventing vehicles going off the edge of the road, and then just a gentle thing that meant the vehicles were encouraged to kind of stay in lane. So this whole thing wasn't based on lanes. The vehicles were free to go anywhere they wanted across the motorway, but if there was no other reason for them not to, then they'd go straight on. We did have constraints on the actuators, so they'd be within physical limits, and also some terms to discourage, sort of very strong braking or very strong steering. In fact, we cheated a bit, and we particularly penalised braking because we wanted to see that kind of cooperative swerving behaviour. And that's because in a real motorway situation, when you're doing 70 miles an hour, if something bad happens just in front of you, you don't really have time to brake in general. Steering gets you out of trouble in a better way. That's very different from an urban situation where you're driving slowly and you do some calculations about how to avoid collision. Then braking nearly always does work. Now, in our practical demonstrations, the cars, I'm afraid, were going pretty slowly, like 20 or 25 miles an hour, but we wanted them to behave as if they were going down the motorway. So we wanted to encourage cooperative swerving, steering behaviour. So we just turned up the weight of the penalty of braking in our model predictive control optimizer to encourage that steering instead of braking. So the actual cooperation was done via maneuver coordination messages. That's a draft from Etsy. And as far as I don't know of anyone who's used those in real life anywhere else. If there was one thing that this project really succeeded at, it's that it was a very, very clear example of real vehicle-to-vehicle mediated, radio-mediated cooperation amongst vehicles. So exchange these messages that swapped the desired and planned trajectories every 20 milliseconds, which is much faster than we needed to, because actually our solver was quite slow. And the knowledge of what the vehicles could see was shared as well, which we used in demonstrations. And actually Marco did some work on figuring out how we could best use Kalman filters, or a Kalman filter, to combine a vehicle's own knowledge of what it could see with knowledge it learned from another car that would be time delayed. So you might say, oh, I can see a car there, but I've just heard from that other car that can see it better, that 50 milliseconds ago it could see it there. And knowing how to combine those optimally is something that Marco did. So anyway, this wasn't just a theoretical project, it was real. And we went to the Bruntingthorpe Proving Ground to do this. In future, we'd go to Cavway, our own proving ground, once it's built. But here we are at Bruntingthorpe with a nice straight bit of runway and the strange aeroplanes parked around. So we had a safety driver on each vehicle able to take control. And the safety drivers would set up the situation by driving the cars manually. And then when they were side by side, going at the right speed, then they'd press a button on a dead man's handle. And at that point, the computer would be entirely in charge of driving the car. So the steering, braking, acceleration were all under car control. And that's true of both cars side by side, and they're talking. So then they become like a sort of hive mind. Now in control terms, I've told you that we do a lot of electronics in Cambridge. So I don't know if you can see my mouse pointer, but that white box in the back of the car is a unit we built. So that's the sort of main ECU, the main computer in the car. It's built around an NVIDIA GPU module, and it's got loads of I/O for doing automotive stuff. It runs Linux, but also it's got the built-in vehicle-to-vehicle radio and the built-in differential GPS as well. So it kind of had everything we need. And this, we were quite proud of this, because if you look in the back of a lot of research vehicles, they're usually kind of stuffed full of whole, you get a whole rack of computers and bits and pieces held together with cable ties and Ethernet cables and things like that. Whereas we could actually hide all this underneath the boot floor and put our luggage in and drive to the hotel in it. So that was quite good. We had a touch screen in the front, and that kind of showed a picture of what the computers were understanding. So we could understand what they could see, and we could kind of demonstrate that they were using this cooperative planning. The only sensing we had, and this is going to really disappoint you guys in the Autonomous Vehicle Society, I'm sorry, we had one camera behind the rear view mirror, which had a neural network from another partner from Cosworth, and that could identify cars, but actually it didn't really work far enough away to do the main control task. So we used that in some demonstrations, but we generally relied on the cars just telling each other where they were using GPS coordinates. But then it's the cooperation that really mattered. So this was the kind of scenario we set up. So we had two cars side by side, very much like that simulation I just showed you, going down the road, coming up against one obstacle. They do this cooperative swerve that is the first in the world. It's great. And then they'd face a second obstacle and they'd split apart. And I'll show you a video in a second, which is actually the one that we took in development work. It's before it was public. It was kind of less formal. The real thing is on YouTube, the kind of final dissemination event. So that's sort of more glossy production with drone footage and the foam cars and everything. With this one, we're just going around traffic cones, but I hope it gives you a better idea of what it was really like. So I will attempt to play this video.
Three, two, one, go.
Okay, so we're side by side at 20 miles an hour in the two mucker vehicles.
Mucker has control.
They're now fully under computer control with cooperative algorithms running, coordinated by vehicle-to-vehicle communications. Coming from the first obstacle in lane 1, so we expect a cooperative swerve away, which has happened.
Avoiding collision. Yeah, okay. You okay?
Okay.
Yeah.
And now we're facing another obstacle in lane 2. So in this car, yeah, we should swerve away from that, and the other car has gone past in lane 3. That's perfect.
We are going.
Okay.
Yeah.
Okay, we're okay.
Yeah. We're fine.
Okay,
Yo.
okay.
Right, so that's not the kind of glossy, polished version, but hopefully it gives you more of an idea of what it's like being an engineer in the back of the car. You know, we're playing with walkie-talkies and, you know, getting cold in the rain, putting cones out and things like that. But when we were getting cold in the rain, I always told everyone, you're living the dream, because so many people will be jealous of doing a project like this. So here's a plot of where the vehicle actually went. So they sort of did more or less what we expected in that run. The steering actuator outputs and so on. Whoops. And this is really hard to see, actually. Sorry, this is done in Matplotlib. But just thinking again of that simulation I showed you, this blue line there shows the planned trajectory of one of the cars, and the black dots show the desired trajectory. So you can just about see that its desire is to go around the obstacle. The blue line shows that it was planning to go straight towards the obstacle, and that at that instant, communicating that, and over the next couple of iterations, that encouraged the red car to get out of its way. So the algorithm did work. So this wasn't a fix. Because these cars were programmed to kind of help each other, to cooperate, they would actually sometimes surprise us. So here's a picture taken when we were doing the video, the official video. So it's a bit confusing because all of the cars are white, but the ones in the red box are the kind of real mucker cars, the automated cars. And these two white ones are foam cars. They're ADAS targets that you can run into, and they're more expensive than a normal car, but you can put them back together again if you crash them. Although actually we had one older one that kind of blew apart in the wind. It was very windy there. It was very spectacular, and we had everyone out there chasing down the runway to pick up bits of car. Anyway, what I was going to say is that in this example, the cars didn't do what we expected. We started with one inadvertently a little bit ahead of the other. So when they got to the second obstacle, instead of splitting apart as we intended, you know, the one that was slightly behind thought, well, actually, I can just kind of tuck in behind that one. So it didn't do what we expected at all. We were caught out sometimes if they tried to kind of go the wrong way round an obstacle. So maybe they thought, oh, I can squeeze between that and the edge of the road. You know, that's not what we intended. And I even had the experience, I was just driving back up the runway once, and I put the thing briefly into automated mode because we had a bug, which meant it wasn't clearing its last actuator outputs. And suddenly my car just changed lane, and I didn't know why. And it's because the other car was being driven up behind me. So mine had just made way for the one coming up behind us, and it completely surprised me. So So they really were cooperating, and neither car was in charge. So that was the key thing that we achieved here. And as far as we know, that was a first in the world. Now, I've got a couple of slides to see how I'm doing time-wise. I'm doing absolutely fine, actually. I've got a couple of slides on work other than Mucker. Now, I'm afraid I didn't have time to put too much in here. But what I've done is pasted in a couple of video links to things which I can tell you more about as well. So the first thing is, this is another Kia Niro. So it's like the ones we used in Mucker, but this is in the nice sunny proving ground we have in Spain. So if you ever come to work for IDIADA, you might get some trips out to Spain to this lovely sunny place. Get to swim in the sea. It's fantastic. Now this car does have a LiDAR on top, so it's got a bit of sensors, and it's got a second computing engine as well as an IDAPT. So it's got a kind of higher spec. And we're using it to build a demonstrator that's supposed to act as a kind of robo-taxi around our site for kind of taking guests around and things like that. We're also using it to demonstrate kind of ADAS testing and things. And the video I'll show you, it's not the standard video that introduces CavRide. It's one that shows doing some vehicle-in-the-loop simulation. So the principle of this, and it's something that we'll want to do in the UK as well, is that the car is going to be fooled about what's in front of it. So kind of bypassing its perception system, we're just going to tell it that there are some actors there, pedestrians or vehicles, which it will then try and avoid using its kind of ADAS algorithms for automatic braking or steering. So we call that vehicle-in-the-loop simulation. So I'll play this. And I should say, there was a lot in common with Mucker here, so you might see bits and pieces in the video that you'll recognize from the previous Mucker video. So they've got the same kind of screen and started off with the same application.
Vehicle-in-the-loop covers the current gap between simulation and physical test methodologies by integrating a real vehicle into a virtual traffic environment. Thanks to our expertise in advanced simulation tools, we have designed a new virtual testing platform to support the development of ADAS and automated driving. By applying IDIADA's methodology, information from the geolocalization of the vehicle allows us to merge virtual and physical worlds, providing immersive scenarios to the driver. The main applications of vehicle-in-the-loop are the pre-calibration and evaluation of ADAS and automated driving systems. It is also being assessed by Euro NCAP to be included in the vehicle safety rating process, allowing a wider test matrix coverage. A wider range of complex traffic scenarios according to existing and future standards, guaranteeing the driver's safety. Our vehicle-in-the-loop testing is a cost-effective solution that allows ADAS and automated driving systems development and validation in multiple complex scenarios with a high degree of accuracy and repetitiveness. IDIADA has all the necessary know-how and tools to perform vehicle-in-the-loop turnkey programs. Our versatile and modular virtual platform is a tailored solution that adapts to our clients' requirements.
Right, so there are a couple of details there which I should tell you about.
I'm sorry, but I think
we're also looking at for CavWay. And the simulator they were using to kind of move the kind of virtual actors was oh yeah.
I think we missed the details, unfortunately. It seems like your connection is struggling at the moment.
Oh no. Okay.
You can repeat it. I thought it was just a very interesting part.
Okay. Right. So can you hear me now?
Yes.
And your video is frozen also, so maybe you can
Oh,
Yeah, your video is frozen as well, so maybe you can disconnect the camera, I guess.
oh, right. I'm sorry. Were you able to see the YouTube video?
Yeah.
Oh, good. Right. Okay, I'll stop my video. Oh, I got a new router last week. In fact, we've got 2 new routers, so I hope I'll be okay. Oh, I mean, immediately, if you lose me again, and I will go downstairs and find an Ethernet cable to plug into the side of my computer.
Thank you.
So a couple of details there is that we were using the open scenario language to define scenarios, the test scenarios, and it was working with the Carla simulator. So there was actually like a big laptop in the back of that car running Carla, and there's a component of Carla called Scenario Runner. And these are all things we're looking at using on Cavway as well. So, and incidentally, should you get involved in vehicle work at IDIADA, I had to go out there and do a kind of driver training course. I had to go at high speed around the track and do kind of braking on slippery surfaces and do oversteering and stuff. And oh no, I was going to show you I've got a kind of vehicle pass, but I've just turned my video off. Never mind. So anyway, it's good experience going out there. It's an amazing place, and hopefully our own facility here in the UK will be very similar, but less sunny. Right. Okay, so this one is what we're intending for the UK. So the UK government is putting money into connected and automated vehicle testing grounds. And they're not all the same. They want a kind of variety. So some of them are public roads, some of them are kind of private facilities. Some of them are to do with parking, and some of them are to do with kind of urban situations. So we've been given funding to support the building of this proving ground that's all about kind of junctions. So like big motorway junctions. We could also set up kind of smaller junctions. So this is going to be a really big part of the work at IDIADA for the next 10, 20, 30 years or something. It's really going to shift what we do in the UK. So I'll play the video. Again, do just tell me if there are any problems with it.
Cavway is a new connected and automated vehicle proving ground designed and operated by IDIADA together with our consortium partner Prova Developments. It will be based near Oxford in the UK and completed by the end of 2021. What makes Cavway unique is that it will include a comprehensive set of highway junctions, all within a fully connected, controlled, repeatable and safe environment. It will also offer ADAS and automated driving development and validation capabilities according to the latest Euro NCAP and homologation regulation requirements. As for connectivity, Cavway will provide a fully configurable site with V2X, C-V2X, and 4G and 5G coverage, allowing a wide variety of testing possibilities for development and validation projects. At Cavway Proving Ground, it will be possible to control everything the vehicle sees and hears in a coordinated way to set up all kinds of tricky edge case traffic scenarios, enabling seamless integration between experimental and virtual development work. Cavway will be a comprehensive, versatile and virtual development site, ready to perform all the required development and validation testing programs for future connected and automated vehicles.
Right, so I should just tell you a couple of kind of technical things about that. So firstly, the IDAPT unit, that white computer I showed you in the back of the mucker cars earlier, that is going to be used as the roadside unit at Cavway. So doing the kind of vehicle to infrastructure communications. So that's something we're working on now. We're doing a load of software work. We've got units set up in the Cambridge lab talking to each other, and we're building new software so that we can get them all to sort of act as a coordinated set. So there's a lot of stuff deploying things in Docker. It's all kind of Linux-based applications that are running. And the simulation environment you saw there, so it's Scala again. And again, it was using some open scenario scripting. And another aspect we saw very briefly was designing the layout. And we kind of designed the track, especially if we want to change it for individual customers, in OpenDrive format. So that's like a kind of industry standard format for sharing maps of, you know, representing road layout, and it includes information like kind of lane widths and lane speed limits and things like that. So, so there's a certain amount of kind of, you know, standard file format use, standard tool use that's really important here. That's partly because we want, you know, if people come to our place to do testing, we want them to then be able to, you know, move that work elsewhere, to be kind of portable, to be interoperable. So timeline-wise, Cavway at the moment is like a load of heaps of gravel in a field near Oxford. So the runway does actually exist because it was an old kind of World War II runway. So there's these kind of concrete areas, but they're not smooth enough to do driving on. So that's all going to be kind of tarmacked according to the plans you saw there. And the idea is that it will be open, at least in part, from the autumn this year. So it should all happen pretty fast now. Certainly by the end of this year, it should be largely open. So you know, anyone working for IDIADA this time next year is bound to be involved in work at Cavway. Right. So so that's all I've got for slides. I didn't want to put too much in. Yeah, it's good to have some time for questions and stuff. I did put a link into the official Mucker video, which is much more glossy. It has the kind of drone footage and stuff, and the foam cars. But the scenario we did in that kind of final video is actually exactly the same. And yeah, I just wanted to emphasize that, you know, it was a real privilege that on Mucker we did get to do something really new. If you kind of search for cooperative vehicle programs where people have actually done cooperation between full-size vehicles, there's very few things. I think I found an example of one where they were doing a sort of cooperative emergence from a T-junction. But as far as we know, we're the first people to do cooperative collision avoidance like that. So that was really cool to do. And I've got a link for Cavway there as well. Well, I failed to put in a link for CavRide, our project in the proving ground in Spain. Right. So let me put my video back on. Okay, I'll hopefully come back to you now. Wearing hourglass, haven't pressed start video. Aha, right. Oh dear. Right, my own, I'll stop sharing.
All right.
Okay, so yeah, that's all the talk I've got prepared, but do hit me with questions. And I really fear your questions because you're a bunch of automotive academics and I'm not, you know, I'm, so you have to go easy on me.
All right, so everyone, you've heard them. Let's start our Q&A session. So if you don't want to talk, just go ahead and type it in the chat, but we do encourage you to speak up if you want to.
Out of interest, can you see me now? I can't see my own.
No, we can't.
Oh, I thought I'm going to move downstairs and plug into an Ethernet cable in case it helps. So don't be alarmed if you see my house scrolling by.
Okay.
Hello, guys.
Hey, Julia.
Let's go plug into the Ethernet cable here. I've got myself some Ethernet. If my video recovers.
No, it doesn't seem the case. I think it's the drivers of the webcam is probably crashed.
Oh no. Oh, actually,
The same problem I have right now, as I mentioned earlier.
link lights on the Ethernet. Hopefully, it might improve things in a sec. I've had so many kind of flawless video.
I think you completely lost connection. We cannot hear you right now.
Oh no.
Oh, we can hear you now.
Oh, great. Sorry.
We still cannot see you.
Zoom itself is saying not responding. This isn't great. Sorry, I was about to say I should drop out and come back in again, but
yeah, sure. You can do it.
Sure.
yeah. Oh, hang on, maybe it's recovered now. It was Zoom itself froze. This never normally happens. I'll just try. Maybe I confused it by plugging into the network.
Now we can still not see you.
Right, I'm so embarrassed. I'm gonna quit the meeting and come back in. I'm really sorry.
Of course. Yeah, no
Of course.
worries.
But okay, this has been to me it's been really interesting to see this project, and I'm also glad that we have now the recorded video so we can go and see them again.
I'll go ahead and pause the recording right now.
Can I go first for a couple of questions?
Yeah, of course.
Yes.
One of them, Charlie, I would like to ask you about your personal journey, how you end up in autonomous vehicle industry, and why you feel passionate about it. What drove you out from chemistry industry into this?
Yeah, it was actually because I've always been a bit of a geek, to be honest. I mean, when I was growing up, I had a home computer when I was 12. It was like a ZX Spectrum, which was, sort of a very early thing. And I always really enjoyed the coding. So during my PhD in chemistry, I actually did quite a lot of numerical simulation. So because I thought maybe I'll go into software. And when I got to the end of my PhD, I thought, I don't really want to carry on with that particular topic. So I'll just try an industrial job as an experiment. And here I am 26 years later. So, I mean, the autonomous vehicle bit really came later. That's obviously where cool stuff was happening. So when there was an opportunity to get involved in this work, I put myself forward and said, I'd love to, get involved in that, and I'd love to lead it. So I kind of volunteered, so I'd get in there. So yeah, it's a good area to get into, I think. Yeah.
I mean, because I recognize how challenging it is to change your career path, and how you can be shaped by your environment, and your experiences can determine your future as well.
Yes, and I mean, I've certainly found that in my office it's kind of a bunch of geeks really, and everyone's very friendly. There isn't a lot of politics or anything, so it's been a fairly conducive atmosphere. I was going to say it's can be quite academic, but actually it's not entirely like that, because unlike academia, we're not always chasing for grant applications. Although actually it's similar, because we do have to do proposals for commercial work, and in fact Mucker was kind of funded work, so we did have to do a bid for that. So but yeah, no, it's a nice atmosphere.
And second question would be about the Barcelona involvement. How much knowledge transfer has been done from Spain? You mentioned Barcelona into UK.
Oh, yeah.
What is the reason?
Yes, well, they've got more people than us. It's much bigger. So there's like 2,000 people in Barcelona or something, and maybe like, I don't know, 30 people in Cambridge, another 30 people in other bits of IDIADA in the UK. That's a bit of a guess. I'm out of date. Mm-hmm. So they've got a bigger team, but because they've been doing related work, we've swapped various bits and pieces. So they've, we shared our Mucker software with them so they could get their vehicle going, and they've shared kind of simulator and scripting techniques with us. So we do kind of trade, and things don't always necessarily fit perfectly, because projects tend to diverge in their nature. But where at least we can learn from them with techniques and stuff, then we do. And oh yeah, oh yeah, sorry, I was going to say what I meant to show you when my video failed earlier is that I did get this coveted level D, which is the most basic driving permit for driving on the high-speed track. So I had to get that before I was allowed to do the mucker testing. So it was a fun couple of days doing the training course down there in Barcelona.
I had a question. If somebody...
Then I would also have a couple of them. So you first, and then I go.
So like you talked about it, so can this be implemented in existing cars? Because cars these days have inbuilt cameras and LiDAR sensors and all sort of things. So,
yeah, it's interesting. I mean, you hit on exactly what my stock answer would be, is that you couldn't do mucker. It wouldn't be economically viable to do a mucker type thing in vehicles that were completely conventional, because they wouldn't have the sensors, they wouldn't have the actuators. But if you've got a vehicle that's already automated, then it's just a software feature. I mean, it does need the vehicle-to-vehicle radio as well. So if we imagine in the future that we have, connected and automated vehicles around, then it just becomes a software feature that you could add, a sort of emergency cooperative function. But yeah, but it'd be way too expensive to kind of retrofit a normal car just for something that may never be used. You might drive for 10 years with a car and never face a crisis where you need to cooperate. So it wouldn't be worth the hardware cost of doing it just for that.
So the hardware point of view, so every different level of autonomy has different sensors. So if a car is, suppose, if we talk about Teslas, they have LiDAR sensors and a lot of autonomy. So do you think the Mooka software could be, used there?
Yeah, potentially. And actually, I know that Elon Musk is really anti-LiDAR, isn't he? He believes in cameras and maybe believes in having a couple of radars. He doesn't like LiDAR at all. But I mean, so long as the sensor set gives you a kind of surround view, then it can work. And you also need good kind of downrange view. You need to see quite a way down the road, so that if you're driving at highway speeds, you can anticipate things that are 2 or 3 seconds away at least, and that turns into like 150 meters or something. So given that, it is possible. And I must say, I'm amazed what's going on with the Tesla full self-driving beta. If you kind of go on YouTube, and there are people kind of letting their cars drive them around in America, and they're kind of using all their customers as guinea pigs. I don't think you could get away with doing that in the UK, but they seem to be getting away with doing it over there. And to be fair, the people doing the videos always say, as a disclaimer, I'm on the beta program and I'm kind of looking after this thing the whole time. But we were so risk averse in mucker compared to that we had highly trained test drivers, the kind of people who are used to kind of driving cars sideways for a living for films and stuff. And we had a special safety architecture so that if the car ever decided to steer too sharply, we would cancel the automatic function so that it couldn't catch the driver out. And that's, I suppose, because we had kind of prototype software we didn't really trust, because validating software to a high level is an expensive and time-consuming game. But even so, yeah, it seems pretty risky what they're doing. But at the same time, it's an approach that is achieving what they need ultimately. Well, there's an argument about whether you get the last few % of what you need for real self-driving safety.
Thank you.
I have a couple of questions now.
Sure.
The first one is, okay, first of all, it really amazes me about the Mooka project how a set of vehicles, each one with a different dynamics, a different inertia, and different, let's say, behaviors can cooperate together in a swarm to modify the trajectories.
Yeah.
Because of course, each vehicle with each different dynamics means different allowable trajectories and different allowable steering angles. And so to me, it really amazes me how the vehicles can cooperate together to one common new trajectory. And my question is, has it been tried to make the vehicles react with a longer or shorter planning horizon Then
Yeah, I mean, we did kind of mess around with that a bit. It would be a bit grand to say we optimized it, but we did our best to make it work reasonably well. If you make the horizon too long, then the numerical solver takes too long to solve, and you can also get kind of unstable solutions with kind of wiggles in and things like that. So it actually worked reasonably well with just with a horizon with a fairly small number of points, because then it could solve it fast enough. It was still actually pretty slow. It was like 200 or 300 milliseconds, which, I'm embarrassed about. It's not as fast as you'd expect. And going back to the point of cars with different dynamics and so on, or vehicles, it's true. I mean, for Mucka, we just had 2 identical vehicles, but they were each responsible for computing the trajectories they could achieve. So I suppose if you had a mixed fleet of some sporty vehicles and some goods vehicles that are very slow and can't steer very sharply, then the trajectories they would broadcast would reflect what they thought they could achieve, their own predictions of their abilities. It's interesting, actually, that the place where we did the Mucka filming, and you can see this in the official video, at the very end of the runway, you can see these big trucks going around in circles, and it's where they kind of test to see if they will tip over. So if you're a truck doing evasive maneuvers, you've got to limit your steering so you don't actually fall over, depending on your load.
True. Thank you very much. And my question is, now that the Cowboy is on the way to development, which are the skills and the competencies most needed in the next years, do you think, for IDIADA UK in looking forward to this expansion?
Oh gosh, that's really difficult. There's been quite a range of roles. I mean, I'm sure we'll need people to actually be there with customers, working on testing, helping them set up test scenarios, either in advance as a planning activity and simulation, but also actually on the ground, actually kind of, helping customers set up vehicles with instrumentation, positioning them in scenarios and coordinating things. So there'll be some sort of practical work there, as well as some sort of support functions that can be done offline. But there's also an awful lot of kind of safety work, analysis work, which doesn't really have to be done at Cavway, but it's going to introduce us to more customers who want that kind of thing. That's a real need at the moment, which everyone is finding it hard to recruit for. So that's a big area. Oh. Hey, sorry, I just realized it's getting dark. I you can still see me okay. I can't get up to turn the light on. I'm just going to maximize my laptop brightness. That's the only light I've got in the room. I can't move because now I'm plugged into the Ethernet cable. So yeah, so it's, I suppose there'll be more test engineers in terms of people who can help set up tests and define tests, analyze tests. There'll be more emphasis on testing rather than development so much. But I'm guessing that as kind of engineering services, we will get all kinds of requests to help out in vehicle projects with customers that come along and want to use our facilities. It's always a bit hard to predict what's actually going to come through the door, but yeah. But I'm hoping it means we'll have more real stuff going on, because it'll pull people in who will be interacting with us.
Okay, thank you very much. We have questions in the chat.
Yep.
Oh yeah, right. So I've just seen Aditya's question: how many cars at maximum can be incorporated? In principle, there's no theoretical limit. I mean, in the simple Windows simulation I had, we certainly had 5 sometimes. Obviously, computationally, it does get harder the more vehicles you have. But each vehicle only has to consider the trajectories from the N other vehicles. So the computation time for each vehicle goes up proportionately to the number of other vehicles involved. So if you have like twice as many vehicles, then the computation will take twice as long per car. In the simulation I was running, because it's all being done on one computer, then if I have 5 cars, then it gets 25 times worse, because it's got to do the computations for all of the cars. So then it's kind of order of n squared instead of order of n. In practice, I guess you'd filter it out so that if there were vehicles that were kind of out of range, you would neglect those in your solution. You'd say, that's too far away to really matter. So you'd have to put some limitation on how many you consider. There is another things a latency problem in that it takes time to establish the cooperation. Because if one car says to the other, I want to move, and then the second one says, because that one wants to move, I want to move, it takes a while for the effects to kind of propagate between vehicles, to kind of ripple across. So so that would add some kind of practical limits as well, I guess, to how responsive it would be. But I'm afraid we only tested it for real with 2 cars, because that's all we had.
Okay.
We have another question
from Dinesh, which is a former student of ours, and Dinesh wrote a thesis on trajectory planning last year under Marco. And his question, first of all, thank you, Dinesh, for joining us. And Dinesh's question is, he would like to know about computational requirements for a vehicle to be part of the MACA, and also what trajectory planning algorithm did you use?
Okay, so I mean, computationally, it needed a sort of well, the actual computer was an NVIDIA thing. It had 8 gigs of RAM. It had a GPU, not a very big GPU. In fact, next to me, I've got one somewhere. I've got a development board. Sorry, it's stuck in my cupboard. Used for ages. So so this module there is an NVIDIA Jetson TX2. So that's what we actually used for Mucker. The IDAP units are getting an upgrade now, so they'll get the, thanks, you've spotlighted me. So yeah, so that's the unit. So it's got the cooling fan. I don't think we troubled the cooling fan too much because our computations didn't really use the GPU, except when we were doing the neural network stuff, perception, or for human driver modeling, which we tend to do as a separate activity. So it's like a 6-core CPU, 8 gigs of RAM, I think 32 gigs of hard disk, and it was working moderately hard, but mixing it out. So I think probably have the kind of modules people use for doing kind of real self-driving tend to be quite a lot more powerful than that now. So it wouldn't computational requirement. I'll give you a link actually to the paper, which I can copy from the slides, because we've now published an IEEE paper. So I'm just, oops.
Thank you very much. That would be really great. I will for sure read it.
Yeah, sure. So hang on, I've just accidentally closed my slides. Right. Copy hyperlink. Oops, sorry. So there's the IEEE paper, and there was a much simpler paper, which is just on archive.org as well. I'll put that into.
Okay, thank you very much. We received it. And,
right. Yeah. So the algorithm, I mean, it was like the simple model predictive control, and it was really the terms that went to the cost function that defined the behavior. So having those kind of smooth boxy shapes to repel vehicles so they wouldn't want to overlap, but they were still free to go next to each other. It was really important. We didn't want one car to sort of be deflected from another one if they were in separate lanes. So sorry, I'm getting a load of pixel noise. Let me just try and turn a light on. Right, there's a light that's kind of behind me. I can turn around so I'm illuminated. So yeah, we didn't want cars kind of repelling each other. It's actually a problem we had to start with. So we wanted our cost function to allow cars to pass side by side in adjacent lanes, but obviously we wanted them to repel if they were going to crash into each other. So it was designing that cost function to achieve the important bit, and we used the IPOPT numerical solver, which stands for interior point optimization. So that's a free one. It needs a differentiable function. So our functions were differential.
Oh.
Right.
Okay. I see. I was looking now at the paper, and I see that for the dynamics of the vehicle is used a bicycle model. And,
yeah, kind of. It was very, very simple. I mean, there's a big difference between what Cranfield did as sort of offline modeling activity, which was part of the scope of the wider project, and what we actually implemented in the car. So the dynamics model in the car was very basic, and that's because you know, they were not actually going very fast, so they didn't really need much of a dynamics model. You know, it's not like they were kind of burning rubber or anything. So
okay.
so
No,
yeah.
Generally, I think it works pretty well. The bicycle model at not very high speed.
Yeah, actually, I'm trying to think now. I don't think we actually had that running when we were doing the demos. I think we just had a simple model of it, kind of like running on rails. You know, like I'm losing my terminology. Like, you know, a sort of kinetic model. So it wasn't really a model at all, really. It was, you know, just a sort of prediction, just an extrapolation.
Okay.
But it was good enough for this demo. But again, if you're doing this for real in high-speed vehicles, then you would want a proper dynamics model that would take account of kind of tire slippage and even skidding, because, you know, if you're 70 miles an hour in the wet, you wanted your vehicle to steer as hard as it could without kind of losing it, then for sure you'd need a more advanced dynamics model. So, I mean, there's a whole load of areas of compromise when you're doing a real project like this between what you'd ideally do if you were doing it in production and what you can actually do given the limited time and money and software engineers when you're trying to make something real work within a short time. So what we actually implemented was relatively basic, just so we could kind of show the ideas of cooperation. What you'd need to do in production it'd be a much more careful job. It would have to be kind of properly specified and validated and so on. It would need international standards to coordinate it between different vehicles. You know, it'd be an enormous effort. And it would be more advanced academically in terms of the modeling. And it would need a better solver, you know, a faster solver, a decent perception system, which, you know, our perception was very basic, and yeah, we kind of mainly used just GPS positioning. So
okay.
We have more questions in the chat. So Prajwal asks how immediate decisions are made considering the extreme scenario of traffic in autonomous vehicles. Means that what we need to consider in terms of sensor data and actuators.
Right. So how many decisions made? Yeah, I mean, in the real, so I don't know if you mean in kind of real autonomous vehicles compared to what we were doing. Because I suppose that's kind of confidential. We don't know what's happening inside a Tesla or an Uber vehicle because they don't publish it. But we do know that obviously they will do full braking up to the limit of tire friction and enough to actuate ABS if they detect an obstacle they can't avoid, which all cars have to have now anyway for automatic emergency braking. So certainly on Mucker, you know, the worst case scenarios would be collision scenarios. So our cost function would make allowance for how hard we hit other vehicles. So there's a sort of simple term that was basically based on kinetic energy with a term for kind of how quickly we were going as well. So it would rather kind of sideswipe another vehicle, just kind of knock into it sideways, that wouldn't have too much kinetic energy liberation. That would be preferred over kind of going head on into something. So you can certainly decide what to do in extreme scenarios on that basis. If your cost function knows what a bad crash is compared to a minor crash is, then you can aim to have the minor crash if you have to. And that's what we wanted to do. But yeah, what happens in real robo-taxi programs and some of these US giants, we don't really know.
We have another question from Tiga. So he's asking, the efficiency of MUCA algorithm actually depends on the number of autonomous vehicles which have the software installed.
Yes, absolutely. So we were imagining this scenario for those demonstrations where every vehicle has mucker, and that would never happen in the real world unless it was regulated. But these things do come along. When I was first learning to drive, the car I drove didn't have ABS. Now you can't buy a car without ABS. You can't buy a car without stability control. I've got a 14-year-old car, and I paid extra to have stability control on that because I knew that you were like half as likely to die in your car if you had it or something. Actually, I think it was a US statistic where they have top-heavy cars. But and now, of course, automatic emergency braking is mandatory. You get these increases in safety level that come from regulation, and also they're kind of forced on the manufacturers through kind of grading through the Euro NCAP scheme and stuff. They want to look good, so they have to add these safety features. So it's not impossible that, given a few years, that the regulators, starting with the United Nations and going downwards, would say you must now add cooperative collision avoidance. Until you did that, in practice, you'd never expect to have very many of these vehicles next to each other at any one time. But even if you only got one vehicle alone, even if there isn't really any cooperative aspect, the other part of mucker, which Cranfield was responsible for, was the prediction of human-driven vehicle trajectories. And so it should also do its best to avoid where it thinks other vehicles are going. And if you're in a vehicle that's got all-round perception, so it knows there's a vehicle over your left shoulder that's about to come past you and one over your right shoulder that's maybe not about to come past you, you can maybe still make better decisions than a human can and avoid accidents that a human might not be able to avoid by using an automated system, even without the actual cooperative bit. Though it's the cooperative bit that we really wanted to demonstrate, of course. So I don't know if that answers your question. But...
Yes, thank you so much.
No worries.
I don't think we have any more questions in the chat, but if somebody wants to ask any questions, they can probably send us and we can redirect it to you, or we can mail you as well.
Sure, yes. The slides, I'll email you a PDF copy as well, which is a bit smaller than the PowerPoint copy, and do feel free to distribute those. It's got my email address on the last slide and some links to videos and whatnot.
Okay, thank you very much.
One last question to Charlie.
Sure, Marco.
I know him very well, but I don't often have opportunity to talk about the project again. Well, first of all, you said that the IDAPT board there's something else that's coming up on that regard, and I don't know whether you can disclose any detail, but you mentioned that there's a second revision.
Oh, sorry. What was I talking about? Oh,
maybe I'm wrong.
Yeah, was I talking about automatic emergency braking being coming
No,
up?
I thought you showed us a board, which was probably a prototype of the board.
Sorry, no. Yeah, actually the one I showed you, it was just a development board. Yeah. I know what you're talking about now. Sorry, Marco. This is the original development board with a Jetson TX2, but which we used in the existing IDAPTs that we had on mucker. But we're upgrading that to be the NVIDIA Xavier, which is much more powerful. It's got a bigger GPU and faster cores and more memory and things like that.
Yeah.
So we'll have
we have one actually in Cranfield. We have two of them in Cranfield, so that we know them fairly well.
I went to an NVIDIA GTC conference, or twice in Munich, I think it was, and so the marketing machine got to me, and I thought we should have some of those. And now, of course, they've got the Orin ones, which will be even more powerful. But we'll have these Xavier ones anyway.
You know, I'm always very interested in this product because I think it's very useful to have an integrated ECU instead of just the pure NVIDIA processor, which is what NVIDIA sells at the moment. We need all of the other components. So
yes, and some stuff which nobody really talks about, but it's useful. Things just like analog inputs and digital outputs, so you can turn some things on and off and stuff like that. With maybe a half an amp or something. It's kind of really basic automotive stuff that I suppose we understand from our background with like lower level ECUs, because used to working with engine controllers and body controllers and things like that.
Absolutely.
But you need that kind of stuff as well, and plenty of CAN buses and things.
Yeah, that's why we have the cars full of boxes, unfortunately.
Yeah.
And that's why your cars look a lot tidier. And the last very quick question. What have you done with the 2 Muka cars?
Oh, we've still
1
got
year.
them. Yeah. So not much, but we still have them, and we're going to start using them. They will go to Cavway, I'm sure, and we'll somehow use them in demonstrations. I'm afraid we haven't actually done any development work with them. I mean, partly because the pandemic started just as we finished Muka. We were so lucky getting all of our track work done just before, lockdown started. So they spent a lot of time just sat outside. I'm afraid one of them's got strange electrical behavior because we think the wiring's eaten by rats, which actually caused us a lot of trouble during the filming.
My car has all sorts of issues after 1 year outside without being used. I fully understand. Thank you very much, Charlie.
But we still got them. Yeah, no worries.
That's very good to know.
Can I ask one more question about the Jetson video board? Because I have experience of using the TX2 before as well. Well, I've always encountered the lack of performance, such as the CPU performance is actually very slow. Like you do the cost map, the update rate could only be 10 Hertz. Well, I don't think it can be handled the real-time high speed autonomous trajectory planning, actually, because I've been using that for some robotics project. But well, I try to increase the cost map update rate to update my trajectory planning, but however the CPU just run too slow. But yeah, so I wonder, can TX2 can be the embed board you use for the Muka ECU?
Yeah, I mean, that's all we had then. And I mean, now the Xavier's kind of replaced it and would give some more performance. But I think maybe a more fundamental problem is that the optimizer was really, I suppose, intended for kind of academic work and stuff, maybe not for real-time execution. There's a whole load of GPU bandwidth available that isn't being used. I can't help wondering if there'd be some way of using that for kind of parallel computations when doing numerical optimization in MPC. So, I mean, I suppose it was another thing where it was good enough for what we did for our demonstrations. For sure, I wasn't that satisfied with the overall performance.
Would you think about using the NVIDIA PX2, which is normally I think it's designed for the autonomous solution, right? The NVIDIA PX2, which I saw people using that before as well in some autonomous cars.
Right. Oh, is that the one with the Orin modules? I think maybe. So you've got TX2, then Xavier, and then Orin is above that. I think. I'm not sure.
Yeah, the PX2. Yeah, should be.
Yeah. I mean, for sure, there's better hardware available now. I mean, we started this like 3 years ago, and the world has changed since then. So, and the world will continue to change, I'm sure. That's but there is a cost as well. But the whole point of Muka, I suppose, is that you'd only implement it on a car that already had some sort of automated driving functions, and so you'll probably already have a pretty decent computer to do that with. So yeah, it's true that a TX2 isn't the kind of state of the art for doing a full self-driving vehicle, but it was good enough for this application.
Thank you.
No worries.
Hello, sir. Hello, am I audible?
Oh yeah, I can hear you.
Yes, sir. So my question is in terms of the dynamics of vehicle. So as we are developing the algorithms using the simple bicycle model or the quarter car model, so how you are upgrading this to an actual scenarios, means the practical testing of the vehicle on the roads. So how you are shifting from those quarter car model or simple bicycle model to such a algorithm or a control unit which can handle automatic braking system and all other actuators?
Right. Well, I'm afraid the honest truth is that we're not actually doing further development work on it right now, because unfortunately we can't do that without money and time, and so we need an excuse. We can't just spend our own money and time on it. If there was another funding opportunity, then we could do further development. If there was a customer who came along and said, "We'll give you £1 million. Can you develop this and make it better?" Then we would. As it is, I'm afraid it hasn't progressed any further. So we only had the extremely simple dynamics model that we used in the real vehicle, but there were those better models. So Marco's colleagues, especially Hussein Kantrwala, who's moved on now. He's just gone back to India. In fact, he did some really advanced stuff with models with a lot of degrees of freedom to try and really have kind of high fidelity representation of how the vehicle would move on the road. So I can see that's the kind of direction you'd go in if you were doing this for real and wanted to test it at the limits of performance. But no, unfortunately, we're just not doing that because we haven't got the time and money.
Yes, fine, thank you.
Okay, if there are no other questions.
Yeah, I guess we can wrap this up. So again, well, not again, I hadn't said this, but on behalf of everyone, thank you so much for coming and sharing this presentation with us. I'm sure everyone that came found it very insightful. And it was a pleasure. Thank you for coming.
Oh, thank you so much. It's a pleasure to be invited. And I'm so sorry about my wretched broadband messing things up.